My name is Tommaso Frassetto and I will be presenting our paper VoltPawn, Attacking x86 Processor Integrity from Software. This paper is a joint work with my colleagues at Technische University of Darmstadt in Germany and researchers from UC Irvine in California. The purpose of this paper is to abuse software available hardware interfaces in order to inject faults in running SGX enclaves. This is a software-controlled fault injection attack that requires no kind of hardware modification or physical access to be performed. Moreover, we do not rely on any kind of side-channel leakage. The reason why those attacks are possible is that modern processors have a very tight power and thermal budgets and thus very stringent constraints in both areas. Thus, they allow operating systems to control both voltage and frequency in order to maximize battery life and prevent overheating. However, this is a problem if the operating system itself is malicious. A similar attack was shown possible 3 years ago here at USENIX Security by the Clockscrew paper that managed to influence the execution of a trust zone environment inside an ARM processor of a mobile phone. However, it is challenging and non-trivial to perform the same attack on an x86 processor, as ARM and Intel processors have a number of differences. For example, on ARM, the voltage and frequency can be set independently and freely, while on x86, the operating system can only choose between a set of predefined and well-tested pairs of frequencies and voltage. Moreover, on ARM, each core can be set independently from each other, while on Intel x86, all the cores share the voltage and frequency. This means that the attacker script runs in the same conditions as the victim, which means that it might also be subject to faults. Moreover, ARM interfaces for voltage and frequency are all documented, while Intel ones are not all documented, which means we had to resort to other sources of information and also reverse engineering ourselves. Finally, Intel processors have a feature called machine check architecture, which has the goal of identifying and fixing errors at runtime in order to prevent hardware malfunctions from resulting in wrong data being used by the program, which is exactly the opposite of what we want to happen. So we had to overcome all of those. Normally, x86 processors choose automatically the best frequency and voltage for the current execution mode. However, the operating system can also decide to disable this automatic system and pick between one of the frequency voltage combinations provided by Intel. Those combinations are called p-states and can be chosen by writing to a specific model-specific register, which is only accessible to the operating system. This MSR is defined by Intel and documented. However, there is also an additional interface that allows the operating system to apply an offset to the voltage. This interface requires writing to undocumented model-specific register, which is known in the community as OC mailbox. By combining those two interfaces, the attacker can choose any frequency from one of the p-states and apply a negative offset in order to undervolt the processor and induce faults. In a VoltPawn attack, we assume the kernel is malicious, and we want to attack the only thing that the operating system does not normally have access to, namely an SGX enclave. Specifically, we want the SGX enclave to return the wrong data for some specific computation. For those of you who are not familiar with SGX, SGX is Intel's implementation of a concept called trusted execution environment. The idea is that even if you have a malicious application and a malicious operating system kernel, you can still have a trusted component run in a hardware-protected environment that is supposed to run independently from interference from any other system or software component. Unfortunately, we showed that for Intel SGX, this promise is not completely fulfilled. Our initial analysis was performed by trying all the p-states that Intel makes available and then gradually reducing the voltage provided to the processor. What we noticed is that at the beginning, some errors would show up, but they would be corrected by the machine check architecture. If we reduce the voltage too much, the system would crash or freeze, which is not good for the attacker because it would lead to drawing attention to it. However, in the middle of those two areas, there is a window where faults are not caught by the machine check architecture, and thus computation goes on with faulty data. We performed a detailed analysis of the location of faults during vector computation. For every core in 3 different processors, we analyzed 1000 faults, and this graph shows their location inside a vector register. We can see, for example, the first core shows almost all faults are concentrated in one location, while for this other core, all locations are almost equally affected by the fault. This is very useful for the attacker because they can choose which core to run the attack on in order to maximize the effectiveness for their target. We then performed an additional analysis to understand which kind of instructions are more likely to receive faulty data in an undervolted environment. We found this specific code pattern to be specifically prone to it. There is a vector XOR or add or similar instruction followed by a move of the data used by the previous instructions to memory. This is used a lot in cryptographic code, which is of course very interesting for an attacker. After our analysis, we can finally mount our attack. We start the victim SGX enclave on one core and our attack script on a different core. We move all the system processes and every other process to the attack core in order to reduce interference on the victim. Moreover, we want to increase contention with the CPU resources on the victim core in order to increase likelihood of fault. To do this, we introduce a stressor program on the logical partner of the victim core, that is, the other logical core on the same physical core. On the other hand, we do not want contention on the attacker core, thus we keep its logical partner idle. Stressors are small snippets of code that are executed as often as possible in order to increase contention. We analyzed a number of them and this is the best performing one. In this stressor there is first a push to memory, then twice a shift left instruction in vector registers, and finally a pop from memory. In order to prove the effectiveness of our attack against real-world code, we created an SGX enclave which computes the HMAC of a 32-bit string using the SHA-256 algorithm. We used Intel's own OpenSSL version that was designed specifically for SGX enclaves. In this case, the attacker's goal is to force the enclave to return the wrong result for the HMAC, which is interesting, for example, in the case of blockchains, to convince the enclave that a signature is not valid when in fact it is. We ran this attack on 2 of our processors and reported in this graph the success rate for every core. We can see for the first core of the processor on the right that the average success rate is 96%, and on some runs it went as high as 99%, while on the second core of the processor on the left, the average success rate was 20% and it went as high as 34% on some runs. Thus, for every processor, there is at least one core where we can successfully inject faults. We responsibly disclosed our findings to Intel in August of 2019, and they subsequently confirmed the validity of our findings. They also released in December of the same year a mitigation that includes 2 components: a BIOS patch that allows the user to disable access to the OC mailbox that we abused in order to undervolt the processor, and a microcode update that includes the state of that flag in the SGX attestation report. That way, a remote third party can refuse to communicate with an SGX enclave running in an insecure configuration. Concurrently to our work, a different team worked on a similar project that was eventually published under the name Plundervolt. Plundervolt also targets SGX enclaves by undervolting the processor. However, there is a number of differences between our work and theirs. First and foremost, we focus on vector instructions, while Plundervolt focuses on integer multiplication and AES instructions. We suspect that the faults that we discover in the vector instructions are actually the root cause for the faults that they describe in the AES instructions. While we focus on desktop processors, the Plundervolt paper focuses on laptop processors. Finally, they do not analyze the effect of stressors while running undervolted code. This concludes my presentation of the VoltPawn paper, the first one together with concurrent work to successfully compromise the integrity of SGX enclaves. We have performed a detailed analysis of the faults happening in an undervolted environment under a number of conditions, including voltage, frequency, and temperature. More details about those are in the paper. Moreover, we have performed an attack on real-world code and show success rates up to 99%. Thank you for your attention.